Dear students, welcome back to our NPTEL online certification course on analog electronic circuit. Myself Pradeep Mandal from EE and EC department of IIT Kharagpur. Today's topic of discussion, it is single-ended to differential signaling and basic models of differential amplifier. In fact, this is continuation of our previous lecture. So, we are going to continue on the basic model of differential amplifier. If you see the overall plan, we are in module 7 and we are continuing the first two items of module 7, and in the overall structure wise we are at the module levels of the circuits. In fact, as I said that it can be considered differential amplifier, it can be considered either block level or module level depending on the perspective. And in this course, we are focusing this topic differential amplifier as module level discussion. Okay. Now, the concepts we are planning to cover here, it is the following. So, yesterday or in the previous course, in fact, previous lecture, we have discussed about numerical examples. So, we will continue some more numerical examples, and based on the basic model of differential amplifier to highlight what are the importances of different performance parameters of the differential amplifier. After that, we will be talking about the motivation of using differential amplifier. So, we are expecting after the first topic, we are expecting that we will be having fair understanding of the behavior of differential amplifier, and then we will be talking about where and when we need to use differential amplifier. Particularly, we already have discussed about single ended amplifier. So, we have to discuss about the situation where single ended amplifier may not be the preferred one, rather we want differential amplifier. And then we will be talking about different variants of differential amplifier, starting from the basic one which we have we already have started, and then we will be talking about which variants of the amplifier should be used in what condition, right. So, coming to the topic we have discussed in the previous class, namely the basic model of differential amplifier, we can consider this is a recapitulation of whatever we have discussed in the previous lecture. Here we do have the differential amplifier. As I said that the input port, it is differential in nature, output port is also differential. We do have the main supply voltage, and then we are feeding the signal at the input port by say two single ended signal, and then at the output we are observing the output either at individual terminal, output terminal with respect to ground, or more appropriate way to say that we can observe the signal in the differential form. And then as we have discussed in linear single ended amplifiers linearization. So, this differential amplifier can be linearized, and so we do have the linear model here of the differential amplifier, and then at the input either we can think of that we do have one pair of single ended signal, or we may consider that it is carrying differential signal and maybe it is having also common mode signal. So, we can represent this pair of signal in this form, namely in terms of common mode component and the differential component. And we have discussed that why we prefer this representation of the signal, input signal, namely because the behavior of this amplifier, differential amplifier, it can be well characterized if we convert the signal in the form of differential signal and common mode signal, and then we can say what may be the corresponding output we get out of this circuit. And also we have discussed about 4 important performance matrices, namely differential mode gain, common mode gain, and then differential to common mode gain, and then common mode to differential mode gain. As you may recall, the differential mode gain, it is defined as output differential by input differential, assuming that the common mode signal it is 0, V in C equals to 0. So, likewise we can define the common mode gain, which is V O C divided by V in C when differential component of the input, namely V in D equals to 0. So, likewise if we consider the other 2 parameters, namely differential to common mode gain, which is defined as the differential signal is getting converted into common mode, that means V O C divided by V in D, when we do have the V in C equals to 0. So, likewise we can define this this parameter, namely A C D equals to, so this is converting the common mode signal in the form of differential. So, this is V O D by V in C when we do have a situation where input differential signal equals to 0. And as I said that this parameter, it is very dangerous thing, particularly we should pay a lot of attention. So, that this parameter should be as small as possible, ideally should be 0. That is because it converts common mode signal in the form of differential signal. And whenever we are talking about differential amplifier, its basic purpose here it is to appreciate the differential signal and also to suppress this common mode part. Now, if the differential signal it is coming as is in the form of differential, then there is no problem. If the common mode signal it is coming here, then also it is okay, but then this output we may not be able to really separate this unwanted signal. So, in summary, this parameter we want this should be as small as possible, ideally should be 0. On the other hand, if say AC or ADC, if they are non-zero, but then we may say that we can put one more differential amplifier to further suppress the unwanted part and we compare to the wanted part, namely differential part, or we can say that we can appreciate the differential part and then we can suppress the common mode part. So, this is what we have discussed in the previous class, and let we go for some numerical example. So, yeah. So, here in this numerical example, we are going to start with the linearized model. So, we do have the main circuit here. and the input we are applying here, which are given here in terms of say differential part and common mode part. So, if you see here both the signals are having two frequency component. So, depending on this t, so this part, first part, it is having a frequency of 1 by t and its amplitude it is 50 millivolt. So, this is of course unit, it is volt. On the other hand, if you see the second part, if you consider the second part, it is having a frequency which is 1 by 4 t and its amplitude it is 0.5 volt, that means 500 millivolt. So, on the other hand, if you see the second signal, its differential part or the first component, if you see, it is also having the same frequency of 1 by capital T and its amplitude it is 50 millivolt, but it is having a minus sign. And so, if I take the difference of say V 1 minus V 2, V in 1 minus V in 2 to get the differential output V in D. So, what we are getting it is 0.1 sin 2 pi by capital T into T. So, these two part, the other higher frequency part, this part and this part, since they do have the same sign, once we subtract this two input, they are getting cancelled out. So, we can say that differential input, it is having 100 millivolt amplitude and the frequency of 1 by capital T. On the other hand, if I take the average of these two signals, if I take average of the two signals to get the common mode component, namely V in C, so that is equal to V in 1 plus V in 2 by 2, and this is equal to 0.5 sin 2 pi by 4 capital T into T, and its frequency it is of course, if I call f 2 is equal to 1 by 4 t. So, this unwanted signal or common mode signal, it is having a frequency 1/4 of whatever the wanted signal or differential signal. Now, once we have this signal pair V in 1 and V in 2 represented in terms of V in D and V in C, then probably we can represent the stimulus in this form, where this signal it is summation of V in C plus V in D by 2. So, this is the V in C part and then this is the V in D by 2 part, and the signal coming at this point on the other hand, we do have V in C and then minus V in D by 2. So, this is the common mode part and then we do have minus V in D by 2, it is given here, right. So, once we get this information, particularly the signals are getting represented in the form of differential part and common mode part, then probably we can look for the signal coming out of the differential amplifier by considering its corresponding parameters. So, what are the parameters we do have? We are expecting it will be having a differential mode gain and then common mode gain and the other two parameters. Now, suppose we will be considering different cases, and to start with ideally we want this circuit should be having differential gain should be as high as possible, and then the other parameter should be as small as possible. So, to start with, let you consider say case 0 or ideal case, where differential gain it is 40, and let we assume that the other parameters are 0. So, if that is the case, and we like to know what will be the corresponding output. Either you can think of the output signal in the form of differential part and common mode part, or maybe we can think of the individual signal with respect to common node. So, either it may be in this single ended form or maybe in this differential form. Okay. Now, we will be talking about that, namely once we have this information of say differential gain 40. So, from that we can say that VOD equals to AD into V in D, right, and that is coming. So, we can multiply this the signal with 40. So, that gives us 4 sin 2 pi by capital T into small t. So, which means that at this differential port we obtain a signal having a frequency f 1 which is equal to 1 by capital T, and its amplitude it is it got increased from 100 millivolt to 4 volt, right. And if you see the common mode part on the other hand, VOC, since the AC we are assuming that AC is not given to us. So, we can assume that this is 0, and in fact, we can consider ADC equals to 0 and ACD it is also 0. So, if I consider all of them are 0, then we can say that this is the Scholl V out, and VOC of course, it becomes 0. So, that gives us the individual signal, namely VO1. So, that gives us the VO1, let me use this space. So, VO1 equals to, now we can convert this this representation of the output information in terms of a pair of single ended signal, namely VO1 equals to VOC plus VOD by 2, which is equal to 2 sin 2 pi by capital T into T. So, likewise, if I consider the other signal, namely VO2, so that is equal to VOC minus VOD by 2, and that is equal to minus 2 sin 2 pi T by capital T. So, this is what the signal we are getting here. So, as I said that this is ideal case. So, we want this block should be intelligent enough. So, this block should be intelligent enough which supposed to appreciate the differential part, namely it should amplify the differential signal and it should completely ignore this common mode signal. So, pictorially let us see what is its the corresponding input and output, and how we can further explain that what is the basic motivation of using this differential amplifier. So, here probably we can so we can use this graph. So, I have prepared this graph so that we can probably sketch the waveform. Say for example, if you want to sketch say V in 1 and V in 2, and since we do have this signal which is 10 times higher than this signal, probably the scale we can consider here, it is say this is 0 and this is maybe say 0.5, right, and the signal here it is having a frequency of 1 by 4t. So, we can consider this is the time period. So, this we consider capital 4 times capital T, this is 2t, this is t, and this is 3t, and so and so. Now, if we consider the common mode part, so this part which is there for both the signals, so it may be having amplitude of this much. So, the signal should be going through this point, this point, this point, this point, and this point. So, let me consider the common mode part, and then if I consider the differential part. So, if I consider only this part and its amplitude is just 1/10 of this, which means that its amplitude should be only one of the scale. So, this part, so it is having different frequency, sorry, this should be having a period of t. So, it should be going like this, and it is having in fact 4 cycles, right. So, this is the differential part, I should say rather half of the differential part, and if I consider the other half of the differential part which is having minus sign. So, this is just complementary of the red colored signal. Okay. So, we do have the differential part, it is represented here, and if I take the difference of these two signal, it is essentially the wanted part which we like to process or amplify, and on the other hand this blue color part we like to eliminate, and this is this can be done by this differential amplifier which is having a gain which is 40, and this is actually differential gain. So, which is amplifying this signal. Now, in the so if I consider the total signal, of course, if I consider this total signal, it is a combination of this blue and the red. So, let me try to sketch that. So, if I combine this blue and red, and if we see the signal coming like this, let me use red color just to represent it better. Right, and then here here we go. So, this red color is essentially V in 1. On the other hand, if I consider say V in 2, let me use pink color. So, if I consider this part, so I need to add this pink color signal with the blue one. So, I do have the signal going like this. And so, if I see the individual signal, we can see that compared to the blue line, the differential part, it is really small, and it may be scary how we can really separate it out, this wanted part from the unwanted part, right. So, this violet color, pink color, this pink color is V in 2. Now, out of this we also say that we have considered the V out, particularly differential part, which is 4 sin 2 pi by capital T by into T. So, let us try to sketch that in the next slide. Yeah. So, we do have the input signal we are keeping as is, and we are trying to sketch the we are trying to sketch the output. Now, when we will be sketching the output, we may recall that V in D equals to 0.1 sin 2 pi by T small t, and that gives us V O D equals to 4 sin 2 pi by capital T into small t, right. And from that we obtained V O 1 equals to half of this V O D, which is 2 sin 2 pi by capital T into small t, and the V O 2 equals to minus 2 sin 2 pi T into small t. And let us use this graph to sketch these two output. And so, here we do have the time axis, and here we do have the output signal can be plotted along this y axis. So, if we consider say V O 1 and its amplitude, it is 2 volt. So, in this graph probably we can consider this is 2, this is 1, this is 0, and so and so. So, the V O 1, which is having a frequency 1 by capital T, and let us consider the same time scale. So, we do have T, 2 T, 3 T and 4 T, and we do have the signal V O 1, which is having an amplitude of 2 and the time period of capital T. So, which means that V O 1, its sketch it is like this. So, it is having an amplitude of 2 volt and a frequency of 1 by capital T. Right. On the other hand, if I consider the other output, namely V O 2. So, let you consider V O 2. So, that signal it is coming just complementary of it. Right, and now we can see that the signal, whatever we are looking for, that got nicely amplified. And the unwanted signal it is completely getting removed. So, if as I said that we are looking for this part or whatever this part, shaded part which is wanted, that part it is coming here with nice amplification. Note that this scale and this scale, they are different. In fact, if you are putting in the same scale, obviously this signal could have been much bigger. Okay. So, that is the basic purpose of this differential amplifier, namely suppressing the unwanted part, which is probably it is having some reason, somehow it sneaks into the signal and it is trying to corrupt the signal, but then we do have this magic block called differential amplifier, which is helping us to completely suppress that. Now, practically, however, this common mode gain AC need not be 0. In fact, the other parameters may also be having some significant value. So, let us try to see what may be the consequence when you have a situation where common mode gain it is non-zero, along with the differential gain may be remaining as high as 40. Okay. So, now here we do have a situation, sorry, I am trying to return this waveform, so that you can appreciate that what are the things it has happened in between or earlier what was the situation. Now, if you see I have changed the condition, namely now we are considering a second or case 1 we say, where it is not ideal situation, namely this is non-zero, and since it is non-zero, we are expecting that there will be some difference in this output signal, or to be more precise, this common mode signal, the blue color signal, it may be having some influence on this part. So, in the next exercise what we are going to do, it is basically trying to see what will be the corresponding individual output, and then I must say that once you have say clean nice output, probably one of them is good enough to extract the information, but in case if we have say common mode gain which is non-zero, then probably the signal coming here either VO1 or VO2 may not be as clean as what we are plotting here. Instead, it still may be having some unwanted signal. So, let us try to see in this situation what may be the unwanted component. Okay. So, let me take a small break and then we will come back.